Welcome to the second talk of today. It is my great pleasure to introduce Professor Małgorzata Bogdan from the Institute of Mathematics of University of Wrocław. She got a master degree in '92 in applied mathematics, then PhD in '96 in mathematical statistics, and in 2009 habilitation computer science, and then the title of the professor given by the president of Poland in 2020. So you see, we have a wide range of interests and quite interdisciplinary career, as it should be, and is highly appreciated. And in 2020, she also got the Hugo Steinhaus Prize in Applied Mathematics. That's the prize of Polish Mathematical Society. Małgorzata Bogdan was a Fulbright professor at Stanford University, and then visitor at Stanford University of Washington, and currently he's a guest professor at the Lund University. She is a leader of the mathematical statistics group in Wrocław. So we'll be hearing about statistics, mathematical statistics, or rather applied statistics. So the simple example of statistical reasoning is that we like to estimate some feature, some trait of the population, of the individual. So we make several experiments, and then we just average these experiments, and usually we get the unbiased estimator. So here the situation is much more complicated, because the number of features, traces, or the number of genes that we probably hear will be big, enormous, and the number of experiments of data is smaller. Okay, so we obviously have a problem, and that's why we need Małgorzata Bogdan to teach us what to do in this problem. So she designed many algorithms dealing with this high-dimensional data, large data, and we'll learn probably about that specifically in biology setups. So the Zoom is yours.
So thank you very much. Thank you very much to Professor to the organizers for inviting me, and thank you to Professor Miękisz for a very nice introduction. So let me just share my screen. Okay. So can you see my slides now?
Yes.
Okay, so I'm going to talk about the regularization methods in the analysis of large data sets. And I will start from the basics, about linear regression. Then I'm going to talk about several regularization techniques, starting from ridge regression, then about Lasso, least absolute shrinkage and selection operator. And if time permits, I'm going to talk about the sorted L1 penalized estimator, which is actually invented and investigated in our group. So let me just explain what type of structures we are working on and what type of problems we are working on. So as Professor Miękisz said, my major field of application is genetics, but today I don't want, because combining mathematics with genetics can be a little bit difficult for readers to understand. Let me just explain what we do on the example of a database, which is maybe easier to understand. So this database is a real database which we got from the hospital in Paris. So in this hospital, they took measurements for about 20,000 patients who went like major trauma. You can see the accident types on the left-hand side. They fall from some height. They were burned by a fire. There was a traffic accident. So we have accident types. We have many characteristics measured for each of these patients, like 250 measurements, some standard ones like age, sex, blood pressure, but also much more of medical measurements. So the purpose of this experiment, basically we as statisticians got the task from the workers in the hospital, but we use these measurements to predict the number of platelets. So the number of platelets, this is the characteristic of the blood, which is very important in making the decision how the patient should be treated after he or she arrives in the hospital. And this is a measurement which is very difficult to take, basically impossible to take in the ambulance. So our goal was to choose among these 250 measurements some which could be used as a good and build a model which would allow. Question?
Maybe if you switch off the video, maybe the voice transmission will be better. I don't know.
Okay, let me just try. So I just stop
because
video.
We have really problems with hearing you.
Yes, but yes, can you hear me now? Can you hear me now?
I can hear you.
Can you hear?
Probably the same.
So when I switch my audio, you also cannot hear me.
So let's continue then.
Yeah. So can I ask some of the participants which are online if they can hear me well?
I can hear you well.
Yes,
okay,
ma'am, I can hear you.
Okay, so I think the problem is in the. So I will just, as suggested by Professor Damek, I will just continue.
Yes, please continue.
Okay. So we try to predict the number of platelets. So this is the characteristic which is very important and very difficult to measure in the ambulance. What you can see also in this database that we have some missing values, but I'm not going to address this problem during this talk. So we as statisticians are supposed to be able to create models also in the situation when there are missing data. Okay, so our objective is to develop models to help emergency doctors to make decisions. So we have some measurements and we want to predict number of platelets using this database. So build a model and tell the doctors you should measure this and this and this in the ambulance and this and give a function based on these measurements which would allow us to predict the number of platelets. The challenge is how to select these relevant measures. So let me just start from a very simple technique, which maybe some of you have heard about, which is called the linear regression. So in the linear regression, we have this is a standard notation by Y. We denote the vector of response variable. These are the platelets counts, okay, in our situation, because this is the response variable is the variable which we want to predict. And we have measurements for n individuals. In our case, it is like 10,000s. And then we have X. X is a matrix. So this matrix you can see in here, okay? So we have as many rows here as we have patients. So for example, here we have two patients which got a knife accident, two patients which had a traffic accident. So each row is a patient. And in each column, we have measurements like age, sex, and so on. And this forms our X matrix. As you can see, in this matrix, some values are numeric, some are text, okay? Like sex is denoted by M and F, accident type by falling and fire. We have techniques which allow us to code these variables which are let's say expressed as text in terms of numbers. We create dummy variables which allow us to represent this variable in terms of numbers, and we end up with something which we call the design matrix. This is a matrix which contains numbers. Numbers which I is the number of denotes the index of an individual, J denotes the index of a variable. So the dimension is n by p. N is the number of individuals, p is the number of variables. So we know y, we know x, and our goal is to estimate or to predict vector beta of regression coefficients. And we assume that the relationship between our y and our x is a linear regression. Okay, so this is the simplest possible model, very often accurate enough to decide which variables are important, which are not. Sometimes not as good for prediction. So we have a linear model. We basically say that our y for a given individual is some linear combination of measurements for this individual. So number of places is some linear combination of other variables. Plus we have a noise. Plus we have a random noise, which we denote by epsilon I. So, and we have n of such equations. So we have an equation for each individual. And when we can write it in a matrix form, y, this is now a vector, is equal to x, a design matrix times beta plus epsilon. And in this data set, actually the situation was such that the sample size, so n, the number of individuals, was actually substantially larger than the number of measurements. But in many applications like those in which I am working, like in genetics, very often n is comparable, p, the number of variables is comparable or larger than the sample size. And such data sets where p is large, so the number of variables is large, sometimes larger than the sample size, we call high dimensional data. So these are high dimensional data. Okay, and now, so let's for now reduce the attention to the situation when n is larger than p. So we have more individuals than variables. In this situation, the standard technique to fit such a model is called the least squares techniques. We simply estimate this vector beta. We pick this vector beta in such a way that we minimize the square of the Euclidean distance between the vector of response variable in our trait data set and the prediction of this variable, x times beta. Okay, so this is, we minimize this vector beta such, we pick this vector beta such that we minimize this L2 norm. And what it really means, okay, so we basically look for a linear combination of columns of x, which gives us the best, which is the closest to the vector y and L2 norm. Basically, it means that we project the vector y on the column, on the space spanned by the columns of x. So we simply do the orthogonal projection. Our x beta hat will be an orthogonal projection of y on the space spanned by the column of x's. And so we know what is, how y hat is our prediction. How our y hat depends on the values which we have in the database. So this x prime, x inverse, x prime is the projection matrix. So, and we can use this formula in case when rank of x is p, when x prime x is invertible. Okay, so now when we compare this formula for y hat by a projection formula to the formula that y hat is equal to x beta hat ls, then you can get a formula for beta hat, which is like what you can see in here, x prime x inverse, x prime y. And now, please note that the only randomness, so if you look at our linear model, x's are fixed, betas are fixed regression coefficients. The only randomness which comes to our model is through epsilon. And we assume that the epsilons have a normal distribution, they are independent, with mean equal to 0 and the variance equal to sigma squared. So because of this, our y vector also has a normal distribution. The expected value is x beta, and the covariance matrix is sigma squared times identity. And now when we look at this formula for beta hat, x's are fixed, we easily get a formula that beta, these estimates have a normal distribution with expected value beta and such a covariance matrix, x sigma square, x prime, x inverse. So what do we know about this estimator? First thing we know that it is unbiased. It is unbiased because the expected value of this estimator is equal to beta. So the estimator indeed oscillates around the true value beta, and it has some, we have a covariance matrix here, so clearly the values of this estimator has some, we can find variances for each regression coefficients on the diagonal of this matrix. So Eva, I can see that you are trying to do something, so I cannot hear you.
Oh, thank you, Małgosia. Thank you that you asked me. The problem is with our main lecture room. So everybody went to, everybody is now at laptops, you know. We went to our rooms and I try to listen from my room. So the point is not with internet connection to Bandlevo, but the point is with the lecture room.
Okay.
So, and the lecture is recorded, so everything is fine, Małgosia. Don't worry, for you and people online and people who are at laptops, you know, it's great. So you may continue.
I can continue from, so I don't have to return, I don't have to repeat anything.
No, you don't need to repeat anything.
Okay, so what do we know about the least squares estimator of beta? We know that it is the best linear unbiased estimator. Linear means that the beta hat coefficient is obtained by some linear transformation of a vector of y, and it is also unbiased. So among all unbiased linear estimator, this estimator has the smallest mean square error. So in statistics, we want to have our estimators to be as close to the true values, beta in our case, and we measure it by the expected value of the square of the L2 norm of the distance between beta hat and beta. So this estimator is the best among unbiased linear estimators in terms of this mean square error. So
question.
There is a question?
Yes.
Sure.
So where do you put in the assumption that n is strictly larger p?
Where do I need this assumption?
Yes.
I need this assumption for the uniqueness. Okay, because in case when if the rank of x is if basically p is larger than n, if x is not invertible, if x prime x is not invertible, okay, but you have infinitely many solutions to this you know, to this problem. You cannot calculate x prime x inverse, and there are infinitely. So you then use generalized inverse matrices, and then you are going to have infinitely many solutions.
Okay. So you're working with the Penrose generalized inverse.
Yes.
Okay. Thank you.
Yes. Yeah. So for the uniqueness of this estimator, if you want to have, we call it identifiability. Okay. So the model is identifiable. The estimator is unique only in case when n is larger than p.
Thank you.
Okay. And now you want to decide which of the variables is important or not. So we statisticians do tests, okay? So when you want to decide which variable is important, which is not, you have a look at this estimate. So clearly what you can see, the distribution of beta hat is normal. So it's probability that you are going to get 0 is 0. Okay, so even when your true beta is 0, your estimator will basically never be equal to 0. So, so we take this estimator and we divide it over its standard deviation. And if this ratio is large, we are going to say that variable is probably important. Probably beta I is really different from 0. How do we decide on this value, how large zeta has to be? Well, in case when beta I is 0, then this ZI has a standard normal distribution. Okay, so what do? We basically pick the critical value. So we say that variable is important, beta I is different from 0, if the absolute value of ZI, of this statistic, is larger than the quantile of the normal distribution and the quantile of the standard normal distribution, and the quantile is picked in such a way that probability that you are going to make an error, that the absolute value is going to be larger than this quantity in case when beta I is 0 is 5%. And this 5% we call a significance level. So I used 5% now. Clearly, you can use your own significance level. Significance level is a kind of we call it type 1 error. It's a probability that you are going to make a mistake in case when in beta I is 0. So this is probability, we call it, of a false discovery. When beta I is 0 and you say, okay, this variable is important, you make a false discovery and we pick a critical value such that the probability of this false discovery is at the level is equal to 5%. Okay. And now what problem where we see a problem with the database being large? When the database is large, when P is large, well, it's high dimensional, not large, but high dimensional. High dimensional means P is large. So what happens when P is large? It happens that the elements of the diagonal of X prime X inverse typically become very large. So you already had a lecture about random matrices. So in practice, in statistical practice, our X matrix is random. Okay, we take the sample from the population, and in this way, our X matrix is really like randomly select from the population. And to investigate the properties of these estimators, we often use idealized mathematical models. So let's assume that all elements on our X matrix are independent from the standard normal distribution. But it turns out that X prime X matrix has a Wishart distribution, and the elements on this diagonal have the expected value equal to n. Okay. So now we need the inverse. So our covariance matrix is just the inverse of X prime X. And it turns out that this inverse has the inverse Wishart distribution. And you might expect that in case when the elements on the diagonal of X prime X are n, maybe on the inverse that will be 1 over n. It is not far from being true, but what you can really see that the elements of this diagonal of the X prime X, let me recall again, the element of the diagonal of X prime X are the variances of the estimators of your beta I's. It turns out that they are equal to 1 over n minus p minus 1. So you can see a problem here, where p becomes large. When p approaches n, these values increase. So when these values increase, what happens? Our variances of betas increase. So the mean square error, the estimation error is going to increase. And also these elements of X prime X matrix, they fit in the denominator of our formula for the ZI. So ZI is going to become small and you are going to lose that power. Power is a probability that you are going to identify important X. That your that your absolute value of ZI is going to be larger than the critical value in case when beta I is really different from 0. So when these elements of X prime X inverse explode, your ZI is going to become small and you lose a power of identification of important X's. And here is just a numerical calculation for this. So here I calculate mean square error for a single coefficient. In case of a linear regression, all these errors, these mean square errors are the same for every coefficient because they are all unbiased and have the, okay, not really. So here it is the case because we assume that all elements of X are IID from N01. So in this situation, on all these mean square errors are the same for each coefficient. And you can see here n is equal to 500, and with p we approach n. So p increases 100, 200, 300, 400, and you can see how the mean square error explodes. it becomes very large, and your estimator becomes very inaccurate when P becomes large. And here you have a power. So for power, I basically picked the true value of beta such that in case when you have only 10, when P is only 10, the probability that you are going to identify this true important variable is about 90%. And when you increase the dimensionality of your matrix, when you add new variables into your data set, this power diminishes and falls basically below 20%. So as you can see, there is a problem. Okay, so people often think, okay, I can select more and more measurements, I can build my large matrix, I can still calculate least squares estimators, and I can now find out which are important by doing my z-tests. And you shouldn't do this, okay? When P becomes very close to n, the least squares estimators have such a large variance that your power of identification of important x's really is basically almost zero, okay?
Sorry, on this graph, n is still equal to 500, yes?
Yes, n is equal to 500. We increase only P.
Okay, thank you.
Okay. So now we come to the problem, okay? So basically, in case when P is, so first thing is, as your colleague already asked about, when P is larger than n, you simply can no longer calculate least squares estimators because they are not unique. The x prime x is no longer invertible. Another thing, even when n is larger than P, but P is close to n, least squares estimators are basically hopeless, okay? They have a very large variance. So basically what you should do, maybe you should identify important variables. So we do model selection. We want to identify important variables, but not by doing the least squares estimator in the whole, on the whole data. So you basically do it this way, that you look at some small models, and you add some new variables and decide which of these new variables are important, which are not. And very often people look at the residual sum of squares to decide if a model is good. So what is the residual sum of squares? Is the square of the distance between what the values which you observe in your data, your y, and the predictions which are given by your model, y hat. So what problem do we have in here? The problem is that this quantity, this residual sum of square, is not a good, let's say, criterion for deciding which variables to include, which not, because whenever you include a new variable, you simply increase the space over which you, on which you do the projection, and the distance between y and y hat can never increase when you add a new variable. And it usually decreases even when this variable is not important. Okay, so residual sum of squares itself is not a good measure to decide which variable to include or not. So, what we want to do? We want to identify a model which minimizes the prediction error. So how we can approach this problem? I'm now going to give you some theoretical way of investigating which model is good. So let's consider a new sample. So we take a new sample, y star. This new sample, we still have exactly the same design matrix X, which we have in the training sample, the same vector of regression coefficient beta. But what is different is this epsilon term, this random noise. So we take a new sample from the data, and what we want to have, we want to be, well, maybe we don't take the sample. We want to predict this new sample. So we took one sample. Based on this one sample, we predict our y. And we want these predictions to be good in predicting this new sample y star. We want to minimize the expected value of the square of the distance between our predictions and what we are going to see in a new sample. Now, expected value of y is equal to x beta. Let me recall. Okay, so this is the vector x beta. So I can now represent my y star, but mu plus epsilon star minus y hat. Mu is a vector, fixed vector. Epsilon star is a random vector, and y hat is a random vector, and these two vectors are independent because y hat was calculated based on the training sample, and epsilon star is a new independent vector of noise. So this prediction error can be basically written, so because these two vectors are independent, we can write it down as the expected value of mu minus y hat square plus n sigma square. N sigma square is the expected value of the square of epsilon star. And this n sigma square, you cannot beat. So you cannot be absolutely accurate in your predictions because epsilon star is a new vector which you cannot really predict. So this is the thing which you cannot beat. But what you can do, you can try your y hat to be as close as possible to this mu, unknown mu, x beta. But when you look at the residual sum of squares, it's not really the distance between y hat and mu, it's the distance between y hat and y which you observe in your data set. So if you optimize residual sum of squares, you are going to have a problem of the overfitting. You are fitting your model to this specific epsilon which was in the training set, and you lose generalization problem. You lose properties of generalization. So what we really want, we want to have y hat to be close to mu, not to y which you observe in the training sample. What is interesting though, is that the knowledge of residual sum of squares allows us to basically estimate this prediction error. So let me just give you some very well-known result, which is actually quite easy to compute, but I'm not going to do it in this lecture. So if you consider a linear estimator y hat, which is equal to, here we have some matrix M times y, it turns out that this prediction error is equal to the expected value of a residual sum of squares plus 2 times sigma squared times the trace of this matrix M. So this is, as I say, not very difficult result. I think at your level, I should be able to prove this, but it would take me like 10 to 15 minutes, so I just skip this. In case when you use the least squares estimator, when M is the projection matrix, then the trace of this matrix is simply the rank of X. And if the rank of X is P, then the prediction error is residual sum of squares plus 2 times sigma squared P. So now when I want to decide if I should include a new variable or not, I simply add this variable, see by how much residual sum of squares dropped down. And if it dropped down by the value which is larger than 2 sigma squared, then I'm going to add this new variable. If it doesn't, then I'm not going to add the new variable, I'm stopping. Okay? So this is the criterion minimizing this quantity. Residual sum of squares plus 2 times sigma squared P is actually very well known in statistics. It's called Akaike information criterion, developed in '74. And this is one of the criterion which you can use to select variables for your model. Okay, now I'm going to go to the regularization techniques. What problems do we have right now? The problem is that the number of all possible regression models is 2 to the power P. Okay, so because each model can be written as the binary sequence 0, 1, when you plus 1 in place of variable which you include into the model, 0 for these variables which you don't include. So the total number of such sequences is 2 to the power P. And there are basically no good ways of looking through this whole subsets of possible models which I can create from my p-dimensional design matrix. Identifying the model which optimizes Akaike information criterion is actually NP hard. So there are no good solutions which would, so we use many heuristics. I'm not going to talk about it right now. So we deal with this problem in practice. We use many heuristic solutions, but if you use heuristic solution, you never have a certainty that you really identified the model which has the optimal value of AIC. You can have a pretty good model, but basically you never have a guarantee that the model is really optimal. So now the solution is, so here you have a penalty. So we have a penalty. We basically say, I'm going to pick a model for which residual sum of squares is the smallest, and I'm having a penalty for the model dimension, which is 2 times sigma square p, where p is the dimension of a model. Now I'm going to replace this penalty with a convex penalty function. And the first criterion of this type is called the ridge regression, when this penalty is simply the square of a L2 norm of a vector beta multiplied by some constant. We call it gamma. This constant is called a tuning parameter. Okay, and now basically you can see this function, which we minimize, is in beta, it is a convex function. And actually it is also differentiable. So I can calculate the derivative of this LB function. I can compare the derivative to 0, and this is my solution. So my new estimator beta hat, beta ridge regression is x prime x plus gamma I inverse x prime y. So the first thing which you can see is that this estimator can be calculated and is unique even when x prime x is not invertible. So by adding gamma on the diagonal of this matrix, we make it invertible even when p is larger than n. So you can calculate ridge regression estimators uniquely even when p is larger than n. So this is the first thing. But let me just say, but what we can observe is that expected value of this estimator. So again, this first part is this is a linear. Again, this estimator is again linear. X matrix is fixed. Gamma is a known constant. So expected value of this estimator is x prime x plus gamma I inverse x prime x beta. It is no longer beta. Okay, so this estimator is biased. And typically, so does it make any sense that I'm now going to use a bias estimator? It turns out that it makes sense because by introducing this bias, I also reduce the variance of this estimator. And in this way, in many situations, my mean square error is going to be smaller than the error of the least squares, even in case when n is larger than p. So the question is, when the mean square error of my new estimator is smaller than the error of a least squares estimator. And again, let me just now talk about an idealized mathematical example when x prime x is identity. So this is a situation, we call it orthogonal design. There are some specific applications when you can meet such designs, but let's say this is like mathematical abstraction at this moment. So in this situation, the ridge estimator is simply equal to 1 over 1 plus gamma of a least square estimator. It's a little bit smaller. You multiply least square estimator by a constant, which is a little bit smaller. Which is a little bit smaller than 1. And in this way, we introduce bias, but also we decrease the variance. And in this situation, you can do quite basic calculations to see that the ridge estimator always has a mean square error smaller than the least squares in case when the beta vector is small, when the L2 norm square over L2 norm of beta is smaller than p sigma square. And otherwise, you can select gamma small enough that your ridge estimator will be better than least squares. So we can, by using the ridge estimator, we can really beat least squares in terms of a mean square error. This technique we call regularization. We intentionally introduce the bias to our estimator for the purpose of reducing variance. We reduce variance and the mean square error is actually better than the error for the least squares. So everything works very well, and this is actually an estimator which is very widely used in practice. But the point is that it is not easy to use this estimator to select variables. It does not do it on its own, okay? Because the distribution of this ridge estimator is again normal. Again, it is not probability that a given covariate will be equal to 0 is 0. So it itself does not perform selection. you have to build tests, and they are a little bit difficult to build because the bias is actually, you know, in case when you don't know the true value of beta, the bias is very difficult to estimate, and building tests on this estimator is not so easy. So let me just now proceed to the regularization techniques which reduce the dimension on their own. And the first of such methods is called Lasso. And in Lasso, we replace L2 norm in the penalty function by L1 norm. L1 norm, let me recall, is just the sum of the absolute values of the elements of beta. So what is the beauty of this? So what is the beauty of this penalty? So first thing is, by doing this, so the beauty of this penalty is that it's not differentiable. It's not differentiable at 0. Whenever the value of at least one coordinate is 0, it's not differentiable. So on the one hand, there is a pain because we do no longer have an analytical solution. We simply cannot calculate the derivative and compare it to 0 to get the solution. So the solutions to this problem, solutions to Lasso, can be found using numerical techniques like gradient descent, and you know, like there are many convex optimization techniques which people develop to do it in an efficient way. But it's a field of statistics on its own, how to design the efficient tools for the convex optimization. But it can be done, okay? So we have efficient tools to do it. But the beauty of the L1 norm is that the fact that it is not differentiable is that it can really reduce the dimension. We can eliminate some beta. This method is going to eliminate some x's on its own. So a little bit of mathematics behind this. So when you have a convex function from P to R, we always can define a subdifferential of this function. So the subdifferential of the function f at the point B is a set of all vectors V such that the difference between f of z and f of b is larger than the inner product between this vector v and z minus b, okay? So this is the definition of a subdifferential. In case when the convex function is differentiable at point b, there is only one such a vector, and the gradient of f. In case when the function is not differentiable, this is a subset, this is a set of vectors. And for example, when we differentiable the absolute, we differentiate the modulo of x, okay, absolute value of x at x0, we have a value. So absolute, the absolute function is differentiable when x is positive, it's 1, the derivative. When x is negative, it's -1. But at the point at 0, the subdifferential is actually the whole interval between -1 and 1. This is the derivative from the left-hand side and from the right-hand side at 0. And now you can see, and another important theorem is the convex optimization function attains a minimum at x0 if and only if 0 belongs to the subdifferential at x0. And you can see that subdifferential at 0 of absolute value is actually the whole interval. So it is a kind of easy for this function to obtain minimum at 0. Minimum at 0 means eliminate some variables which, when we say that when some beta is 0, we eliminate a variable from our model. And here is a little bit more detailed calculations, which maybe I will skip because I think it is not so maybe easy to follow. Again, this calculation is for the situation when the design is orthogonal, x prime x is identity. So then the function which we minimize can be actually broken at the sum of relatively simple functions for each coordinate. So to minimize this function, we minimize this individual function for each coordinates. This individual functions look like this. And when you differentiate them, you can find out that basically the solution is like what you can see in here. So in case when x prime x is identity, you can find the least squares estimator. And it turns out that Lasso is going to make a given coefficient equal to 0 when the least squares estimator is smaller than lambda over 2. Lambda is this tuning parameter by the penalty. And for other cases, it simply subtracts from the absolute value of a least squares estimator lambda over 2. Okay. So this is, you can see a shrinkage in here, and you can see also that the estimator is going to be biased because the least squares estimator is unbiased. When you subtract something from this, we are going to get a biased estimator. But it shrinks towards 0, and in this way, it reduces the variance. Okay, so this estimator actually indeed can make some regression coefficients to be equal to 0, can eliminate some variables from your model. And here is like a picture of how these two, again, this is idealized situation when x prime x is identity. The black line denotes the least squares estimator, and the blue line shows how the reach behaves as a function of, so the reach estimator in this situation, I think I picked lambda equal to 1/2 is basically you multiply least squares estimate. So I selected lambda gamma equal to 1. So I multiply my ordinal least squares estimator by 1/2. This is the blue line. This is the reach regression regularization. We basically shrink everything towards to 0 in such a way, proportionally. When you use Lasso, you subtract lambda over 2, and then when least squares is small enough, your estimator is going to be equal to 0 here. So, and you can a kind of steer, you can decide how many variables you are going to make equal to 0 by playing with this lambda value. When you use lambda large, you are going to eliminate many variables. When one lambda is small, you are going to eliminate less variables. Okay? And there is like the whole research on how to pick lambda such that this estimator has good statistical properties. Okay? So the whole idea, again, is to use regularization, which is not differentiable. When the function is not differentiable at these points, which are at this point of singularities, you can determine this dimensionality reduction by using this non-differentiable estimators. A little bit now, since I'm going to at least spend 10 minutes on slopes, I'm going to quite quickly go through the next slides. So now the question is, can this method really identify the true model? Can this method really tell us which betas are 0, which are not? And here you have a condition which is called a representability condition, which is a very nice mathematical condition, which tells you under which circumstances we can really properly identify the sign of our beta vector. So beta vector has a sign, okay? So sign is again a vector. For each coordinate, it can be equal -1, 0 on 1. If a given coordinate is 0, it's 0. If a given coordinate is negative, the sign is -1. If it is positive, the sign is 1. And I is a set of columns for which beta I is different from 0. I complement is the complement of the set. And here you have a condition. I'm not going to read. You can see this is what sits within a norm is a vector, which you get by multiplying some matrices and the sign vector. You calculate the infinity norm of this vector. And if this infinity norm of this vector is smaller or equal than 1, then basically Lasso can properly identify the model, can properly identify the sign of a beta vector. So it can decide when the zeros are, which variables are positive, which are negative, if only the elements, non-zero elements of beta are large enough in the absolute value. Okay? If this condition is not satisfied, if this infinity norm is larger than 1, then Lasso cannot identify the support. It cannot identify the sign of beta. So this is a very nice mathematical condition. As you can see, it was written in such a way, or quite late in 2009. So this is still an active research over here to really describe properties of Lasso. So we can show that it can identify the sign properly under some circumstances, and it cannot in other circumstances. So, and it is a very nice algebraic condition, as you can see. You can easily check it.
Sorry, I bar appears in this condition only once, yes?
Yes. Yes. Yeah. So what you can see here is like x prime xi. You know, in this first left-hand part, you basically calculate the inner products between these x's which are really important, which are not important. So for the method to be good, you don't want to have large correlation between which ones which are important, which are not important. Okay, so this is the meaning of this x prime x, you know, of this term. Okay, so this condition really is a kind of, so first thing, identifying the vector beta properly, the sign becomes difficult when the vector is not sparse. When you have many non-zero elements, then this SBI vector becomes large. And this condition on the left-hand side is a condition on the correlation within X matrix. When the correlation between X matrix is large, again, it becomes difficult to identify the sign of beta. Okay, this is a very nice condition, and actually, explain new mathematics behind it is at the level of, I would say, first year of a master class in statistics, not very difficult. Maybe I will skip this. So, so I will skip this. I will tell you now about a method, last 8 minutes I have. So this is a method which we developed with our colleagues from Stanford University. And this method is using a different penalty function, which we called a sorted L1 norm. So this penalty does no longer have just one tuning parameter. It has the whole sequence of tuning parameters from the largest to, so lambda 1 is larger than lambda 2 and so on. Then we have a vector beta. We sort absolute values of beta from the largest to the smallest. And we get our sorted L1 norm by multiplying the largest lambda with the largest absolute value of beta and so on. It's very easy to show that this is a convex function, this is a norm. So this is again a convex optimization program which we can execute and find this estimator. We had some statistical motivation to develop this. And I'm going to skip this, okay? So this method was developed such as to control false discovery rate. I'm going to skip this for a moment, okay? This is not so important. These are some nice theoretical mathematical results which it really raised an interest of many researchers who are still investigating this method. It turns out that under many circumstances, it is simply better than Lasso. But what I want to tell you is about the dimensionality reduction. So how this method performs the dimensionality reduction. So, so this method works with a sequence of tuning parameters, and I'm showing you now the balls in this sorted L1 norm in the situation when p is equal to 3. Okay, so I can show it graphically. So first ball here on the left upper side is the ball of Lasso, unit ball of a Lasso norm. Lasso is a specific, let's say, circumstance of specific case of slope when all lambdas are the same. When all lambdas are the same, we are using just one lambda using Lasso. And you can see this diamond shape of this ball, and you can see these singularities, so these sharp edges, which occur when at least one beta is 0. Now, here on the top on the right-hand side, you have the ball in the supremum norm. When only supremum norm is again the case of slope, when only the first lambda is larger than 0. And here you can see edges, so these singularities occur not when some betas are 0, but when some betas are equal to each other. And if you identify that some betas are equal to each other, you don't need to estimate them separately. You also reduce the dimension, okay? So this is also a dimensionality reduction, but in a different way, not setting some betas to be 0, but saying, okay, I know that these betas are equal to each other. I can identify it with my method. So instead of estimating 3 or 4 different betas, I estimate only one by basically clustering variables which have the same beta value. What you have in the bottom is the unit ball in the slope norm when the sequence is decaying. And when the sequence is decaying, you know, like 3 to 1, the edges occur both when some betas are 0 and also when some betas are equal to each other. So the slope adds additional step to the dimensionality reduction by Lasso. Apart from identifying axes for which beta is 0, it can identify those axes for which betas are the same. And we have like a very recent results. So you can again explain all of this by calculating the subdifferential of the slope norm. So we have nice, I think, nice mathematical results, which can show under which circumstances slope can properly identify zeros, but also where can it properly identify the betas which are equal to each other. This formula here in the middle, beta 1, it shows you how you obtain the dimensionality reduction if you can identify that beta 1 is equal to beta 2 is equal to beta 8, and let's say beta 2 is negative to beta 1. Okay. So now all this sum of these 3 variables can be written as the beta. You can replace beta 1, beta 2, beta 8 by just 1 beta 1, and simply replacing all these 3 variables by the linear function x1 minus x2 plus x8. So you reduce the dimension, you replace 3 variables with just 1. And now we have a critical result which shows, again, this is our condition. If this condition is satisfied, I'm not going to talk about details because I'm close to the end of the talk. We can show that slope can properly identify the pattern, identify zeros, and identify betas which are equal to each other. Now, the question is, does it pay off? Does it make sense what we do? Does it help? Does slope help? Is it better than Lasso? This is just to show you that this is a case. This is a situation, first situation when n is p is 200, n is 100, so p is twice as large as n. We have 30 non-zero elements which are all equal to each other. And if you use slope, and they are all equal to 40. When you use slope, all these 40 elements are basically slope identifies that they are equal to each other. And by reducing the dimension, it can estimate this red dot, it can estimate them without error, basically. While Lasso simply cannot identify that they are the same, and it makes mistakes in estimating each singular one because the dimension is larger. So slope has a much better mean square error. It estimates all 40 to be equal to each other, basically without the error. And here is even more difficult example where we have 100 non-zero elements. And here again, slope is basically almost makes no error when Lasso is much worse. So let's summarize the talk. So regularization techniques, they introduce the bias to the estimation by reduce the variance by reducing the dimension a kind of. And in the result, we get a better mean square error, better estimation properties of our estimators, and they are often better in prediction. Okay, and we use in a variety of applications. So I used in the finance applications, in genetic applications. So we have many, and in medicine. So we have many papers about these techniques. If you are interested, please have a look and get an interest in this. Thank you very much.
Well, okay. Jacek, are you there? Jacek Miękisz? Okay, if not, then probably I should play the role of the chairman. So thank you very much for the talk. And I think, okay, are there any questions? Please, Frank Ortel, you would like to ask a question, please.
No, this wasn't a sign for a question, so I just want to give a little applause. Sorry for that.
Applause. Okay.
Thank you very much.
Okay, I didn't understand. Okay. Okay, so are there any questions or comments? Okay, I'm not able to ask a question, so because I missed the beginning, so.
Maybe I have a little question. So
Please.
regarding the different types of norms. So you're working with the L infinity norm, you're working with L1 norm, and you're working with the classical Euclidean norm. So all norms are treated on finite dimensional spaces, and norms on finite dimensional spaces, they are equivalent. Can this be used to look for a criterion which allows to compare the different models?
Yes, yes. So this is how the proofs are working. Okay, so when you compare different norms, when you prove the mathematical results, you can actually you are basically using these types of equivalency conditions. Okay, but in practice they really exhibit very different properties. So particularly when the dimension is large, corresponding to the sample size. So as I told you, the major thing is that these methods have different properties concerning the dimensionality reduction. As I say, in case when n is much larger than p, when we have lots of information and not so large dimension, to some extent, it makes not such a big difference which norm we are using. But in case when you have lots of error, when n is small, p is large, you have this curse of dimensionality. So we don't have much information to estimate each of the coefficients. Then these properties of a norm which I talked about, like different differential, different point of singularities, they, let me just say it. Using a given norm is like using the prior information. So when I have a reason to believe that there are some clusters in my data, then I use slope because I can use this. I can use this property. I can use a better dimensionality reduction. I get better estimates. If, for example, I believe that the model is sparse and there are no clusters, I can use Lasso. If I believe that my model is no sparse, there is no sparsity, but there are many small regression coefficients, then using L2 norm would be the best. So in the high dimensional setup, it's basically, it is no longer such a case that you have one solution which is always the best. Using the specific norm, specific penalty is like using a little bit of a prior information about what type of solutions you expect to see. But yes, again, answering your question, when you prove results, comparing different norms, comparing the rates of convergence of estimators, you are really using the results on the which relate one norm to another one.
Thank you very much. Thank you.
Okay, Małgorzata, can you hear me?
Yes. Mm-hmm.
Okay, because I also have unstable connection. I don't see the lecture room, so probably they don't listen to us right now. Are there any other questions?
Maybe I would like to ask, could you please explain me conceptually about this phenomenon of overfitting? What does it mean that some model is overfitted?
So the model is overfitted in case when it adapts. So let's look again at the linear regression model. Okay. So when you look at the linear regression model, you can see that
But sorry, you are not sharing the screen.
Okay, I'm not sharing the screen, so let me just show the screen.
Okay, now I can see it.
Yeah, okay, so this is a linear regression model, okay? Now, let's imagine that you have P equal to N, and that all column of X are linearly independent. Then basically you can solve a system of equation and you can find a linear, even if these X's are completely not related to your Y. You can solve this equation and you have no error. Y is equal to X beta, okay? So if you add sufficiently many X's, this X beta can at some point absolutely well describe your Y. And we don't really want to describe our Y. Like in statistics, we want to describe this X beta, this mu vector. Okay, so you have to be very, so we want to describe, so let me just go again here. Let me go to this formula in here. So we want our Y hat, our prediction built on our model, to be as close as possible to X beta, where beta is a true value of a regression parameter, not to be as close to Y as possible. So overfitting basically means that you adjust your model to the specific data which you have in the training set. And it means you adjust to the specific epsilon which created this data. While you don't want to adjust to Y, you want to adjust to mu, because if you adjust to mu, if you properly estimate the expected value of Y, you would be able to predict new samples. Are you with me? Am I clear or not?
Yes, I see.
Yeah, when you add new X's, you are simply adjusting more and more to your Y in your training set. And your Y is just a sample from the training set. We don't want to solve a system of linear equation. We want to estimate this unknown mean vector, X beta. Okay,
so
and this
with predictive power, yes?
Yes, exactly. You want to use it later to predict a new sample. A new, like in here, like this whole, you want you want your model to predict this new sample Y star, where you have a completely new error term. And this is a very, very easy actually result. So when I teach classes at the bachelor level, I'm proving this result. This result is also very powerful. You basically are showing that if you use the least squares estimator, your prediction error, so this expected value of this prediction error, this guy, actually depends on the residual sum of squares. It can be estimated by taking residual sum of squares plus 2 times sigma square p. Okay, so adding new variable pays off only in case when residual sum of squares go down by more than 2 sigma square. Okay, so this is a very, very nice result about prediction error. There are many, like analysis of large data sets is a kind of a complicated topic in a way. So this was a very powerful and very important result, but this result also is good to estimate the model, to pick variables, basically only in case when n is substantially larger than p. When p is larger than n, we have additional problems which basically we need to modify this criterion. We need to add extra penalty. I had some research on this. So even in the context of model selection criteria, AKIK information criterion is not a good solution when you have a high-dimensional database. You need to modify even this. Even this penalty here is not sufficient enough to basically tackle the overfitting in case when p is much larger than n. Okay, but at least you see, I hope I explained it a little bit. So clearly, when you add new access to your model, you are going to approximate your Y better and better, and this is overfitting. You overfit to your Y to the specific epsilon, and you want to get generalization property. You want to be able to predict a new sample.
Thank you. Thank you.
Okay, any other questions or comments? Okay, if not, I think we may thank Małgosia again. So, well, I will symbolically clap. Okay.
Yeah.
And well, the lecture has been well recorded. Well, we had some problems with the lecture room in Wędlewo, but the lecture has been well recorded. So anybody can come back to the lecture. Thank you very much. I don't think I can't stop the meeting or recording, but well, we may announce that it's officially ended, okay? So I will leave and I will go to the lecture room and well,